What's up, guys? It's Sparky here. Time for another episode of Sparky's Builds. And today, we are going to be attempting to build an optical encoder. An optical quadrature encoder, as a matter of fact. It's not going to be absolute positioning. It's going to be relative, but let me explain what that is, how it works, uses. I guess I'll start with uses. So an optical encoder is basically something that allows you to measure the velocity and the position of a motor. So you would slide it onto the end of a motor, like, well, this is a stepper motor, but you would slide it onto the end of a motor. So you slide the encoder wheel like onto the end of the motor, and you would have an LED or some sort of light source on one end of the wheel, and like a photo cell, something to actually see the light value on the other end of the wheel. And whenever the light passes through one of the holes on the wheel, this is just an example wheel I have, but whenever the light passes through one of the holes on the wheel, I don't know if you guys can see that, but whenever light would pass through one of the holes, it would increment the value. I'll explain it more in depth when I bring you guys over to the computer screen, but that's the basic idea. That way you can see the position and the velocity of the motor as the motor spins. And the velocity is just by, when it passes its original point, how long it took for it to pass its original point, because it's done a full rotation by then. So, that could be used for, conveyor belts or whatever. That way you know exactly where the part is on the line, and you can do some feedback control, because that's the main purpose of it, is like feedback control systems. That way you can do some feedback control to actually adjust the belt or the robot, or literally whatever else you put it on, so that you can adjust it based on the position that it sees. It knows that it overshot a little bit, and it's like, oh, wait a second, it's supposed to be 12.2 degrees right now. That's mine's not gonna be that good of a resolution, but that's the idea. Oh, it's supposed to be 12.2 degrees right now, but it's 12.8. Let me bring it back to 12.2 real quick. So you use the feedback control, that way it knows from that oh, wait a second, I need to go back and fix it. So that's the general idea. So I'm going to bring you guys over to the computer screen, show you a little bit of pictures, that way you get a better idea of what I'm talking about. And I'm going to show you what I have drawn up in CAD right now. I'm going to code it using Arduino, 3D print it. We'll get into the shebang. So see you guys over in the computer. Let's get it. All right, so to the computer screen here. These are just some notes that I had from a class, actually, that at one point discussed this concept of encoders. So as you can see, we have the wheel with the slots within the wheel, or the disc you could call it, or as it's called here, all right? So you have the disc that has the slots in it, then you have an LED or some sort of light source. I'm going to be using an LED personally, because that's obviously easiest for me. You have an LED that shines through the hole, and then you have a photo sensor that will see the light, and then goes into some sort of squaring circuit. In this case, I'm just going to be using an Arduino for everything. So the Arduino will be reading that basically 1 or 0 value. Well, it won't be 1 and 0 immediately. It's going to be some sort of like serial value, like 0 to 255 or whatever, depending on the intensity of the light that the photocell reads. I'm pretty sure that's how it reads it when you bring it into Arduino. But then I can be, okay, well, if it's above a certain threshold, then make it just 1. Just say it's high. And then I can use that to do some math and actually have it, throw everything out. That way it knows when it's high and when it's low. But I digress. So the point is, it reads that, puts it to a square circuit, it goes through some code, and then you plug in this equation here. So 360 degrees times the number of poles divided by 2. So that's the poles of the motor that you're attaching to the encoder, over the 2 times the number of teeth on this wheel here. So the number of slots on the wheel. So that's how you do just a normal incremental optical encoder. So with that, you're able to just know where it, what degree it is based on the previous degree that it was at. But it's not absolute positioning, which is where you know where it is based off of its home position. So you home it so you have to like home it every time. It won't know where it is in regards to home. It's technically kind of guessing in a sense where it is in regards to home. It just goes, well, I should be 30 degrees off of home based on the amount of slots that I've been through right now. So I guess I'm 30 degrees off of home. Like you can kind of guess a little bit, but it's not absolute. I personally don't even fully understand how absolute works. So it's just relative positioning. But in our case, we're actually going to be going a little bit deeper than just the normal rotary encoder and going into a quadrature encoder, which actually has two rings of disk. So it has an inner ring and an outer ring that are a little bit offset from each other. So with that, as you're able to see here with this, what do you call it, a little signal diagram or whatever, you can see, just goes high, low, high, low, high, low, and they're offset by 90 degrees when it goes high and low for A and B. We'll call the outer one A and the inner one B. Why not? And the thing about quadrature encoders is that you're actually able to tell whether it's going clockwise or counterclockwise, because with just the normal one, all it knows is the amount of degrees. It doesn't know if it's negative or positive degrees, or if clockwise or counterclockwise. It just knows, okay, it's been this many degrees. And if it went backwards, it would actually still, like, if you went forward and then backwards, it would still increment up because it doesn't know what direction it went. So that's what this is for. So by having two wheels here, by knowing which wheel, like which outer wheel or inner wheel, by knowing which series of slots it went through first, it can tell whether it's going forward or backwards. So if it goes through the outer one first and then it goes to the inner one, and then it knows that I think that's clockwise, and vice versa for counterclockwise because they're offset. So that's the basic idea of how it works. So let me bring you into the CAD model I drew for the encoder that I'm going to attempt to build, because the concept, at least to me, it doesn't seem that complicated, but it took me a while to do the CAD actually, because, well, you'll see. It doesn't seem that complicated in theory, but I'm a little worried that it won't work. But whether it does or doesn't work, guys, we're going to have fun with it. Isn't that what this is all about? We're going to have fun and we're going to learn. I'm sure you've already learned so much just by my amazing explanation. But let's head on over to the CAD. All right, so this is the CAD model of our full encoder with everything included. At least in theory, it's supposed to be. I'm hoping that, that I didn't forget anything before I start 3D printing it, but we'll see. So up here is the LCD display that will actually show the degrees on the, for how much the motor has spun, so that you can actually see, okay, because we're getting the data, we need to display it somewhere that you can at least see it. I'm not actually going to be using this for any feedback control system to actually adjust the motor based on the whatever and all that crap, which is what you would actually use it for. I'm just right now, I'm just trying to make one that actually will properly display the degrees. Sending the data over to the motor to get it to actually change based on the amount of degrees that it's going and whether or not you want it to go that far, and et cetera, feedback control systems. That's that's like another video. You feel me? So LCD display on top, and I have it just enclosed on all sides. Actually, this goes a little bit higher. That way it won't fall out, right? Like, the only way it could fall out is if you tilted the entire thing upside down. Actually, that might be, it's fine. Oh, I don't know if I want to actually make it so that it can't fall out by tilting it upside down. Nah, I'm not too worried about it, because it's going to be attached through wires to the stuff in here. So, eh. Plus, I might, let me see, I actually have it over here. No, I don't really want to glue this thing. To it. But that's the LCD display. And then back here, you can actually see in there a little bit, I got the ports and everything. But back here, I have a battery slot. So, oh, that's already fully constrained. But the battery slides in there. It's just a 9-volt battery that should be able to power up everything in regards to the encoder itself. I'd probably use a different battery for the motor, but the motor is like completely separate. Like, you slide the motor into the bottom here. But, yeah, so 9-volt battery, so it can connect to the Arduino, which is inside of here. And this thing actually slides up right now, because this is how you close everything in. So you can actually slide that right in there. So then wires are going to come from, you see I have a little knockout here. So wires are going to come from this part of the LCD display and go into the Arduino. That way it will actually display the values on the LCD display. And then the Arduino is in here. Whoa, that's a dimension. The Arduino's in here. So as you can see, I created just a spot where you can literally just slide the Arduino in and out. So you can slide it in and out. And I just kind of have These are wire leads right here. Yeah, we'll get there in a second. These four little things shooting up, because, and then this right here. So this entire little H bridge thing is for the Arduino to sit on. So the Arduino sits on this in there, and then it can bring wires down from all the pins over here down into this area over here. Here, wait, let me, starting to get a little messy the way I'm angling this. But the pins from the Arduino can go down to these leads over here, right? So you can bring the leads in, or actually these are analog, so they go like over here, I think. But so you can bring the leads over here through this. Again, I have another knockout slot right here. I have this slot right here where it's knocked out from this tube I have down the center. That way you can bring the leads over to the Arduino. And let's see, what else? So, and by the way, this is just the ports for the Arduino right here that you kind of saw on the other side that I have knocked out. Oh, I brought that forward a little bit too far. Yeah, about there. Know how I made these holes bigger than they need to be? It's because it didn't really matter, and I was like, yeah, that's good. Give myself some wiggle room. That's not really a critical dimension. But then down here at the bottom, we have our wheel. So let me slide that out actually. Might be a little too far, but there we go. Let me slide that out. So as you can see with our wheel, it has two sets of rings in here for the slots. So that is just like in the picture that you saw. Here, let me do that. That's just like in the picture you saw. It has two rings in here. So it's got the outer ring and the inner ring, and by knowing which one it passed through first, it'll be able to tell, oh, I know if it's going clockwise or counterclockwise now. You get it. You get it. And over here, these two things right here are the photocells. So as you can see, they're actually a little wide. They're a little wide, but they're just barely not too wide, probably. Because like I said, there is a threshold value that I'm going to figure out what that needs to be. And depending on that threshold value, we'll just say whether it's high or low. So when it's centered on the photocell, right? So like when the slot is centered, you see the other ends of the photocell are mostly blocked off by the dead zones in between. So as long as I make sure to say, okay, well, this threshold value is when it's blocked off on the two sides like that, and you're just seeing the center, the threshold value is, I don't know, 155 out of 255 or whatever the heck it's going to be, and that means it's high. So that this should work fine. If it was any bigger than that, I might run into issues, but that should be fine. And then obviously you have the other one right here. So these are aligned with each other, the two photocells, and then the LED would be here as well. Actually, let me bring the LED over a little bit more. So you would have so this is LED right here. Let's see. Yeah, see, this is the LED. So then the LED would shine onto the photocell, and there would probably be two LEDs. Ooh, actually, yeah, there'd probably be two LEDs. I could do, so here's my thought process, right? I could do one LED, and this one would just have a lower value, like what I said the threshold value to be for high, and it'll probably work the same. I would just be, it would be a little bit more finicky, probably, but it would theoretically work the same. But I could just use one LED, and one of them would just have a higher, or yeah, lower threshold value. Either way, that sentence works either way. But anyway, one of them would have a lower threshold value than the other. So, one of them would trigger at a lower light value because the LED is just going to be further away from it. So, I might just stick with one LED. Might just be easier that way. Because I was just thinking, if I do want to add in the second LED, I need to add like one of these. You see how I have this little knockout? Not knockout. This one's more like an extrusion. I have an extrusion here to actually, you see, mate the photocells too. So the leads will go through the holes on it over here. Leads go through the holes, and then the leads can come out over here, go around, go into the Arduino, and for the LED, it can go around, and you see how I have this this pocket here, just this empty space between the tube. The tube that I have inside this box, there's an empty space here, so I bring the leads inside that empty space, bring it up, bring it to the Arduino, and same deal, right? That way I can actually power the LED. And then what else? Oh, yes. Oh, by the way, this one over here, because I have the empty space on both sides. Here, let me make it a little bit clear. So there's empty space here on both sides of the tube. So that empty space on this side, I'm actually using it that way I can bring the LED lead up to the Arduino. This side, it isn't actually doing anything. I just decided to leave it empty for, symmetry and balance and laziness, and that way I have to use less plastic when I print. You get it. I mean, I guess at the least I could have made it flat here. Like, it still could be empty on the inside, but I could have at least made it flat here. I might do that, actually. That is not hard at all. I could at least make it flat here. Like, not open, I mean. So, like, it'll still be hollow in this portion, but at least it won't be open on the bottom. And then the last thing that's really worth mentioning here is this right here. So this little circle thing is like a basic drawing that I made of a bearing. So with that bearing, I have a little shaft here that goes from that little H bridge that the Arduino sits on. So it connects directly to that, and it shoots down, and then it mates to this radial bearing. Think fidget spinner. Think like a fidget spinner. So it's one of those little fidget spinner bearings, and it goes to the center of that fidget spinner bearing, and then the outside will be able to spin freely. So then, when that outside spins freely, I am then able to, let's mate that. Nope, that's the wrong one. Wait. I am then able to, crap, how did I do this? Oh, wait. It's on the top. I'm stupid. I forgot this little, so the circle here for this this disc, for the encoder disc, is actually smaller than the outer diameter of the bearing. So I made a separate circle on top that just obviously is completely connected to the disc here. So then what I can do is mate that to that. And bada bing, bada boom. So now the encoder disc is, you see, it's not touching the edges of this of the circle that it's in, and it is completely connected to this this radial bearing here. Again, like this fidget spinner bearing. So since the radial bearing spins freely, the wheel disc will as well. So then when the motor connects to this the smaller circle in this wheel disc, and I actually made this circle too big, like it's bigger than it needs to be, but I can make just an easy tubular adapter that will have a bigger hole and a smaller hole on the inside that I can literally just slide into that hole and then slide the motor into that. That way, even though this is too big, I can actually put like different size motors in it, but just by using different size adapters. So that's why I did it that way. I made it bigger than it needs to be for this circle right here. But anyway, the motor would then slide up into that with an adapter that would probably be, like the length as to where it gets to the bottom of this. So it would go all the way from, in here to the bottom here, and then attach to the motor. And then this disc will be able to then spin freely in there without scraping up against the sides or anything. Again, I think I made the sides. Yeah, like that shouldn't touch. Because I'm just trying to think about the detail of the 3D printer. Because if the 3D printer is not detailed enough, then it might still end up touching. But I think that should be fine. So yeah, that's pretty much all there is to it. I say all there is. I just spent like 15 minutes talking about how it works and how I CAD'd it, well, without actually getting into the build yet. But that's pretty much it. Right? That's pretty much it. So that's all there is to how it works. So we're going to try to 3D print this whole shebang up and put it all together, write some code, do some wiring, and hopefully it'll work. Hopefully. If it doesn't work, I will still end the video. And we will call this as a learning experience for everyone involved. So let's get into it.